Yeah, so my thesis was focused on the dynamic temporal aspects of how cities change over time. It's not 100% energy related, but I believe the methods and maybe some research questions are pretty relevant. So happy to introduce some technical and methods we've been working on for the past few years. A little bit of motivation and background for my research is urbanization and the growth of cities is one of the most significant economic transformation. This diagram just shows how fast people start to move to cities, starting from the first industrial revolution. And especially in the last 50 years. And our climate is also changing. This diagram just shows the number of extreme climate events in the last 30 years in the US. The global temperature rise by over 1 degree Celsius. As a result, there are just significantly more extreme climate events. I think the number almost tripled compared with the 80s. And those events are shaping cities. In the last few months, we witnessed the impacts from Hurricane Helene and Hurricane Milton, caused widespread destruction, and people are being displaced, people rebuilding their homes, and we're experiencing those damages at a much higher frequency compared with previous decades. As you can see, there are so many drivers, so many factors that actually change our cities, policies, climate events, gentrification, etc. But how do we understand some specific questions related to those change? Like, are my neighborhoods gentrifying? They're spread out from the settlements, how many buildings were demolished, etc., 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 etc. To answer those questions, we need a building level data. Those building level change can include like reconstruction, abandonment, maintenance. And from the data, we need to understand like maybe the resiliency, the structure, the quality, the energy efficiency of the building. However, collecting those building level data can be quite challenging. Conducting the household survey or inspecting require significant resources. So this is like the overview, like the literature overview of how we measure cities nowadays. Most research use national census for the US. It happens every 10 years. And another source is called American Community Survey. It's an estimated data for every 1 to 5 years. And you have a very comprehensive attributes of social demographics, economics, etc. And some cities and metropolitan areas have their own data sets. New York City, Chicago, Seattle, San Francisco, etc. They publish their building permits, transportation, health-related data. And some utility companies also have. Oh.
Yeah,
Maybe.
okay.
But okay. Oh no.
It might be somewhere here. Yeah, so by days, different measures have some common challenges. Those data are not timely updated. As we saw earlier, it happens every 10 to 5 years. And many of them have very low spatial granularity. It's aggregated, also very costly to collect the data. And many cities have different formats of data, making them different data silos. You cannot do some analysis across different regions. So what is the opportunity? The number one opportunity we saw is satellite imagery. It's becoming more affordable and spatially detailed. The marginal cost of launching satellites, especially high-resolution satellites, are dropping dramatically in the last, especially 10, 15 years, because of the advancements of the rocket industry. And we see startups are providing those 10 centimeters, 50 centimeters satellite imagery updated at very high frequency. And the other opportunity is street view data. This is on-the-ground observation data. And one example is just Google Street View. They have pretty comprehensive coverage of all the US cities. And they update it on sometimes more than once a year, and sometimes maybe for some cities a couple years. But you can see how buildings change over time with street view data. So looking ahead, we believe that both street view and satellites will be more available than today. And on the method side, machine learning are becoming more powerful thanks to the development of all the vision models. But there are some common challenges for machine learning as well. They don't have much pre-trained change detection models, especially for street view imagery. And the existing models, when we tested, they're very susceptible to noisy signals. And it has limited inference efficiency, which is quite important when we do remote sensing tasks. We have sometimes millions, even tens of millions of images. To address those challenges from datasets and methods, we propose some contributions. So we need to first bridge the gap in methods. We need to solve the accuracy issue and the efficiency issue so we can test it on different tasks. And with this machine learning toolbox, it's possible to create this citywide temporal data sets, which in the end will enable us to discover new knowledge of how cities change over time. So I will have 3 chapters for today's talk. The first one is on the ML toolbox we developed. This is on addressing the first gap. And the climate resilience project and the gentrification projects are more on applications. How do we use the toolbox? And we see how buildings change over time and do more analysis at scale. And we have some findings that was previously impossible. I'll first start from the toolbox. So our toolbox has 3 major components. Number 1, change detection for street view imagery. Number 2 is neighborhood level aggregation. And number 3 is multimodal mapping. I'll explain this. First, starting from the change detection. One of the most obvious challenges we have when we try to map change is we need to compare 2 images for the same location, for the same object, essentially. This could be buildings, this could be some kind of energy infrastructure. We need to see how much change happened, whether there's significant change happens, rather than some noisy change like backgrounds, weather, vegetation, things like that. In this case, we need to actually catch there's a new building here. It seems quite obvious for human, but those background noise, if you don't have enough training labels, it can be quite confusing for models to learn. So we proposed this Siamese network, which is previously used in a lot of change detection tasks in satellite imagery. We kind of use similar logics for street views. And most importantly, we provide and downloaded and labeled a very big street view benchmarks for those different cities. It has more than 25,000 pairs of images. Each pair actually corresponds to a building. So this task is trying to tell whether there's significant construction going on for this building. And we provide this larger data sets compared with all the previous benchmarks. After using this data sets, we train this change detection model, and we can visualize how this model makes decisions. For example, if we provide labels on buildings, by visualizing the scalability, which is like the kind of the weights of the AI models, how they paying attention to the inputs. They're paying more attention to the red dots compared with the backgrounds. Here, once we're feeding all the labels for buildings, they're focusing on the buildings rather than the backgrounds. If we have like benchmarks for maybe power poles, we can do like similar visualizations if our models can successfully detect those change. And this is the first step. The second step is once we have this building level observation, what kind of insights can we have for the neighborhood level? Sometimes we need to identify some vulnerable neighborhoods where they have some significant change or they don't have enough like upgrades or improvements. For this neighborhood level, we propose the attention-based aggregation. It's essentially a weighted average aggregation. So you can see the neighborhoods, it's a container of a number of buildings, a number of pairs of images. And what we try to do is, after getting the predictions for each buildings, we need to aggregate it in a weighted average way for this neighborhood and see whether this neighborhood is positive or negative. Previously, people are doing like average pooling or max pooling, different methods. And we propose this weighted average, which we're assigned weights like implicitly for different buildings. And by assigning this attention algorithms, we actually achieve a higher accuracy. And this attention weights are learned like end to end. They can actually assign higher attention weights to like pairs or buildings or points of interest that are more relevant to the final neighborhood prediction and assign less to those less relevant. In this case, we try to see whether a neighborhood is having significant construction. So those like images taken in tunnels and along highways are less relevant compared with images taken on surface streets. Okay, so the third challenge, once we have this building level and neighborhood level predictions, is we need to train separate models for separate tasks. We have like one model for construction, like one model for demolishment, another one detecting like solar PV panels, another one like finding power poles, et cetera, can we actually make those models like more consolidated so we can use like inspired by all the large language model, large vision language model these days? People are just using like one big model for all the different tasks, and we actually do similar things for like vision and like urban sensing, remote sensing space. We look at the existing large language models. We try to test it on our tasks. So you can actually upload an image to, say, ChatGPT and ask questions, say, is there any change from this image to this one? Or are there any like labels you want to predict? You can actually use it to actually help you label. We find two main limitations. Number one is limited accuracy. Those remote sensing images and their associated task descriptions cannot be efficiently collected from the internet at scale. Many of them are in proprietary softwares like Earth Engine and other types of software. So when we try those models out of the box, their accuracy is not as high as our trained models. And number two is limited scalability. They publish their APIs and you can actually call it. It's getting less expensive now. But they still take a significant time. In our case, it's probably a few seconds per image, per query, if we have multiple images in the query. Say if we have millions of images, it would take like a few months or a year to finish the labeling if we don't do any parallelization. So if we want to do it at scale, we still face those challenges. So to address those gaps, we propose number one, large scale remote sensing data, which you can have both text and image. And number two is, this is still work in progress. We try to propose this multi-model encoder, which you don't need to like inference through a large model every time during your tasks. Yeah, so this is the data sets we collected, and we call it SkyScript. This is how we collected the data sets. We downloaded the images from Google Engine, and we downloaded the semantic text from the open source map called OpenStreetMap. So this map is very similar to Google Maps. The only difference is it's open sourced, and you can download a large batch of those geotags, points of interests, like land use, farmland, power source, solar. It's actually pretty good. It's a key value pair, so very granular for the coordinates. And for each image, it is actually like a rectangle of space. You have many those type of tags. You can imagine like there are maybe 10 or 15 tags associated with one image if it's in a place where there are lots of points of interests. And we match them by setting this space constraints for each image. This is like the scale of, on the x-axis, the number of images, and then on the y-axis, it's the number of distinct labels compared with all the previous satellite imagery data sets. So in satellite imagery, the previous benchmarks, they have a lot of images, like they can be on the level of 10 million images, but they don't have a very diverse sets of labels. Many of them have maybe less than 100 labels, most of them. So one of the limitations is we couldn't scale the model, like semantic understanding ability beyond those labels. What we try to do is leveraging the semantic text from OpenStreetMaps and try to expand this y-axis maybe to a few order of magnitudes larger than all the previous benchmarks. So hopefully this model will be understand more objects after training on these data sets. This is like the benchmarks with after training on our SkyScript data sets compared with the original quick model from OpenAI. We designed a few tasks using the evaluation data, the satellite imagery evaluation data. The scene classification, we improve a few points of accuracy. For fine grain classification, we improve around 10 to 20% after training. This is without designing new models. It's just fine-tuning our own data sets to give them like a performance boost. Yeah, so after creating this data set, we were thinking, can we actually increase the inference efficiency? Say, our tasks is something like this: find residential buildings with well-maintained greenery, and you can give them 2 examples. Simply typing this to ChatGPT, nowadays they can give you an answer. Like, it would take a few seconds. Sometimes we need these tasks to be deployed on millions of images. This can be other tasks like find residential buildings with like solar PVs or other type of tasks. We were thinking, can we actually project this task into the embedding space? And we just do it one time. And during inference, we just use this task embedding with the image embedding. We can pre-compute this image embedding. So we can get this prediction logits, which can be quite fast. This is just a matrix multiplication in these steps. So during inference, it can be linear. Why we don't need to pass this task encoder every time in inference. We just pass it one time, keep the embedding, and during inference time, we do it like maybe a couple million times, very fast. So we proposed this encoder-based in context learning. This is some preliminary results. This instruction, the x-axis is the number of images in the task description. And we try to benchmark with just linear probing, which means just linear classification of image embeddings. Adding the test description can increase the accuracy for like pretty much 20 to 10% if we have more than 4 images in that instruction. And yeah, hopefully, if we can get this accuracy higher, like right now, OpenAI's probably do like 80-90% accuracy compared with us, but it just take a long time for inference. If we can reach like similar level, it would be very beneficial for like a variety of tasks we're doing right now. Cool. So moving on, I'll introduce also a work in progress. After introducing the toolbox, this is an application. So how do we use like those change detection inference results to actually have some findings on cities in those extreme climate events? The paper is called Neighborhood Building Environment Disparities Are Amplified During Extreme Weather Recovery. Yeah, so in like climate community, there are actually 2 different hypotheses on what happens after extreme climate events. Number 1 is called segmented withdrawal, a hypothesis that advantaged population, which is more affluent population, are more able to move out of the damaged zones when social vulnerable groups are less mobile. So after the events, richer neighborhoods will be like moving away from its own homes, and like vulnerable neighborhoods have less choices and they are staying in the same place. And the competing hypothesis is called recovery machine. It's assuming that advantaged groups are not moving away from those damaged places. They're rebuilding on their own places, while the non-elites or non-advantaged people are squeezed out because of this after the events. So there are many papers on like deciding or arguing which hypothesis is correct, but most of them are only analyzing like one city or like one disaster. Like after Hurricane Harvey, there are a lot of research on Houston. After Hurricane like Sandy, a lot of research on the New York area. But people haven't looked at this in a longer range on a wider scale. What we try to do is we try to analyze the data for all the like 15 most disastrous events in the U.S. From Hurricane Sandy to Hurricane Harvey, and this is like in terms of dollar amounts, the most damaging nature disasters in the last 15 years. And we create this recovery assessment data sets using Google Street Views for over 100,000 damaged buildings across 23 states, with a total of more than 700,000 studio images. So for those more than 100,000 buildings, each of them, we downloaded this temporal historical street views. Like we make sure that we have street views before and after the events, so we know what happens before the events hits and how the buildings either damaged or recovered or being rebuilt after the events. So those are actually 2 different examples. Number 1, the building was completely demolished after Hurricane Harvey in Houston, and number 2 is a building was actually rebuilt to a better home after Hurricane Sandy. Yeah, so the first thing we do is using the model, the change detection model we introduced earlier, try to tell whether each building was either abandoned or being rebuilt. And we visualize them in the county level. On the left-hand side is the abandonment rate. The darker the red color is, the higher the abandonment rate is. And on the right-hand side is the improvement rates, which the darker the blue color is, the higher the improvements. We find there's some spatial patterns here. Northeast regions like New York, New England, those places are having a much higher improvement rates than regions such as the South, like the Louisiana, Mississippi, those regions. they can sometimes be more than half of the buildings are abandoned, and 40% of them are less than 40% of them are being rebuilt. So we try to see what are the drivers of this disparities. So we look at incomes. We see pretty significant disparities among income groups. Using the census income data, we break the neighborhoods into 3 income buckets: the lower income, middle income, and higher income. And we find that in higher income groups, like more than 80% of the buildings are actually being rebuilt to higher quality, while only 33% of them in lower income, and more than 37% in lower income, when the home is significantly damaged, it's actually being abandoned. And only 7% of them in higher income groups. Yeah, so after this initial analysis, we try to further model this like recovery curve. From the literatures, we see this recovery modeling for like system engineering. After the disruption, you can actually measure the performance. There will be like an interruption phase, and there will be a recovery phase. You can see whether the systems return to the full recovery level or is partial recovery. And we try to do the same thing for each neighborhood. So we see when a home is damaged, one home is damaged in its neighborhoods, we deduct 1 point. If it's abandoned, we don't do anything, we stay there. If it's being rebuilt, like to the same level of the pre-disaster home, we add 1 point after the disruption. If it's being rebuilt to an improved level, we kind of assign an arbitrary number here, like 1.3, where it'd be like 30%. We assume that it's 30% coverage, but we can see some examples that this is kind of the conservative estimation of how homes being rebuilt to a better quality. Most of the times when people decide to build up much better homes, when their previous home was destroyed, it's just at least 50% more expensive than the previous one in most cases when we study it. So this is like an estimate of how homes are improved. And with this modeling, we use the data sets we extracted earlier and the results from the change texture model. We compute this disaster score for each neighborhood, which is a census tract. And this is like taking the average of census tracts in lower income groups, middle income groups, and higher income groups, and see how those neighborhoods are recovering. And you can see in the disruption phase, almost all the neighborhoods are getting like a 25% decrease. And then after maybe 5-6 years, you see the disparities between the income groups. After 12 years, the higher income groups are already recovering to the full level of the pre-disaster status, even exceeding it, while the lower income groups does not reach that, also the middle income groups. So most previous works we see focus on previous, like the pre-disaster status. We use like satellite imagery data measuring change, maybe within a couple-year window. And I think our contribution is this recovery measure over a year.
Yeah, sorry, what constitutes an improved home after? Like, is it more
Yeah.
area?
Yeah, sorry. I didn't quite introduce. We consider a home that has major structural improvements, like the home that are being rebuilt to a higher quality. So we actually categorize improvements just solely based on the images, like from the built environment attributes like facade, the structure, like the size of the homes, the materials, the structural quality of the homes, to determine whether it was being rebuilt either to the same level or a better level. Yeah. There are some other measurements like the poverty value. We didn't take that. Sometimes it's not very significant. Like just from the images, for the scope of this project, we try to limit it to the visuals of each building. So yeah, so this is how we basically measure the visual for each neighborhoods after the events. The disparity in this trajectories made us wonder, are there any underlying financial incentives or financial considerations for different income groups when their homes are destroyed? There are actually two main sources, financial sources. Number one is most people have homeowner and flood insurance. It costs around a few thousands to, in some places, it's getting very expensive. It's getting like 10,000 per year per home. And the policy can cover around a few $100,000 if your homes are totaled. Another source is FEMA assistance programs. This program prioritizes those homes that are underinsured or even uninsured at all. And they can give you a few thousands to, I think the upper limit is 41,000 last year. They probably will increase it this year. They're increasing it every year because they're just more events and inflation, etc. So you can apply to the FEMA programs if you don't have enough coverage from insurance companies. And we do some analysis on like the insurance coverage across different income groups. Number one is the percentage of the FEMA assistance recipients with homeowner insurance. Number two is FEMA assistance recipients with flood insurance. The less people have flood insurance, but higher income groups, more than half of them on average has flood insurance. For home insurance, more than 90% of them in higher income groups have them, but lower income groups only like 40% or less than 20% have those. So there's a gap in resources in terms of the financial you need to support your recovery efforts. And when we do a regression, try to see whether this level of homeowner insurance and flood insurance is positively or negatively correlated with the abandonment rate or improvement rate in each neighborhood. We see this insurance actually have a pretty significant when we do some testing over there. And this is the flood insurance, also follows similar patterns. And once we look at the FEMA assistance amount, we try to see, like the second approach, the FEMA approach, whether it actually helped the vulnerable communities as the policy was designed more towards those communities. So first of all, it's not like allocating more money to lower income groups. Once we do some visualizations here, you can see like across 3 income groups, similar percentage of people are getting like the average amount, which is around like $5,000. And for the top amount, which is 41K last year, actually a higher percentage of higher income group owners are getting those. Our hypothesis is those higher income owners, they probably have more access to like the information or the resources. They're more aware of those resources, so they will be more likely to actually apply for the FEMA fundings. Despite the fact that this FEMA funding was initialized to support the vulnerable communities. Yeah, so after doing some similar correlation with the abandonment rate and improvement rate, we didn't find a strong correlation as the insurance policy with the either attributes. And the other thing is, we find only a very small percentage of homeowners are approved for the top 41K payout, which is not a lot if your home are totaled in those areas. So yeah, so there would be, we think, insufficient financial coverage, especially for low income communities. This is the, I think it's a one time payout. Yeah. So a couple of takeaways. Number one is high income areas we build and tend to improve compared with their pre-disaster status, highlighting the increased disparities with lower income areas. So there are already existing disparities between income groups in terms of their built environment. After experiencing extreme climate events, those disparities can be like increased, enlarged. Number two is insurance policies are more correlated with lower minimum rate, higher improvement rate, while FEMA assistance is not significantly correlated. So we suggest some policy to like focus more on vulnerable communities. And before an event occurs, such as supplementing like some insurance. I know there are some ongoing efforts for like FEMA flood insurance, or I think in the previous administration, there's some supports for lower income communities in those vulnerable areas. We advocate for more those efforts in to help them recover from these events. Okay, so I'll briefly introduce the third projects, which is detecting neighborhood gentrification. Yeah, so in previous projects, we try to see whether a building was damaged or whether it was built to a better quality or equal quality. This project, we try to see the new construction of certain points of interest for gentrification. Like this is the signals that sociologists, urban economics try to catch when they study cities. We try to measure how a neighborhood is changing after maybe some economic developments or some new companies moving in, new group of people moving in, what kind of effects does it have? We try to provide those visual aspects of what kind of impacts like on the ground. And those are two examples. Number one is like a new construction of a new food service restaurants. This can consider to be a very strong signals for gentrification. And sometimes it's not a complete new construction, is like a business conversion from like a local grocery store to like a yoga studio. This is the data sets for this project. We do the analysis across 3 cities. Those are the three of the most gentrifying cities in the US a couple of years ago. And for each dots, each blue dot is actually the coordinates which we collect images. We make sure that earlier image was captured no later than 2010, and the later image was captured no earlier than 2020. So you have this 10-year gap to observe how things change. And yes, this just illustrates the how we collect the data, very similar to the previous one. But here we focus on gentrifying signals. Yeah, so yeah, again, this task can be pretty versatile. Things our method toolbox actually allow you to define your own tasks. If your task is related to energy space, you can do similar things. We are collaborating with Professor Jacqueline Huang from sociology, so this project will focus on gentrification. And after detecting this building level signals, we aggregate it to the neighborhood level, and we can compare which neighborhoods are more gentrifying than others. Yeah, so other experiments we do is comparison with building permits, which is the primary source of data people are using in the gentrification communities. We tell how many constructions going on by looking at how many building permits are neighborhoods. And we test our measures with the building permits with the by correlating with the income growth. It seems our measures have a higher R-square correlation or explainability with the growth of incomes, while the number of permits are just noisier than our measures. After doing this inference for these few cities, we compare our predictions with the existing predictions. So city governments and sociologists, they have their own like labels in mind, like for Oakland, which are the neighborhoods that are gentrifying, and they're very curious to learn what is the discrepancy between our predictions and their own labels. And those yellow neighbors are actually the discrepancies. Our models are predicting those neighborhoods to be gentrifying, but their own like labels from surveys from like sociologists and political governments are not showing gentrifying. So we're looking at these pictures when we find these places are very likely to be some early gentrifying neighborhoods. They're clustered. Sorry. Looking at the pictures, you can see some signals like the new construction of apartment buildings, some new vegetations, and like some new construction of business like restaurants, etc. The main takeaway is using the visual data and the methods we developed, we can provide very up-to-date data to serve as a foundation for policy design. Relying solely on census data might not give us the most updated information for a neighborhood. And another interesting finding, this is like a validation for the existing sociology hypothesis, is already gentrifying neighborhoods can spill over into surrounding neighborhoods. Like we find those neighborhoods tend to be clustered right next to the gentrifying ones. Yeah, so a little summary of the talk here is we developed this machine learning toolbox to give us a high accuracy, versatility, and efficiency for the text and problem research questions we're interested. And using the toolbox, we're able to create a very large scale and granular building level data sets, like those visual insights. The two examples here I gave today are all using street views, but we can do things using satellites as well. I believe methods in satellites are more advanced than street views because satellite data are generally more available than street view data. So more people are developing the state of the art for remote sensing. Of a street view, since right now I believe like 90% of the images are from Google, it's kind of proprietary. It's not 100% accessible to people. We still have some privacy concerns if we can publish those data, but using our models, it's actually possible to create this building level analysis that allow us to have some insights and have more knowledge of how cities change over time. Yeah, so we believe that our methods will provide this to achieve a high granularity and high scalability at the same time. Cool. This is the summary corresponding to the previous initial slides. With this atlas, we're able to mapping this change from all the different drivers, informing the stakeholders, and eventually we're enable us to have a better response to more frequent extreme weather and all the other drivers of urban change. And this is the list of publications and collaborators. And yeah, thank you so much.